Hello and welcome to another lecture of Introduction to Astrophysical Fluids. In this lecture, we discuss the derivation of ideal fluid equations. Previously, as we saw that the moment equations, they are not sufficient to constitute automatically a dynamical theory. Okay, the reason was very simple, that we had 5 moment equations. One was the continuity equation, the other 4 were the 3 components of the equation of the evolution for the linear momentum, and the last one being the equation for the evolution of internal energy epsilon, right? Now we had 14 unknown variables. Okay, so 5 equations and 14 variables. So in case you cannot remember, just we recapitulate that of the 14 variables, we had 6 from the symmetric tensor of pressure, okay, 3 variables from the bulk velocity V, 3 from the heat flux vector Q, 1 for the density N, okay, and 1 for the internal energy density, so that is epsilon. Okay, I mean N or rho, they are just the same. N when it is multiplied by the mass of one single particle, that will give you the massic density. Okay, so we had all total 14 variables, 5 equations. So this does not make sense, because we know that if we have n number of state variables, we need n number of evolution equation for each of the state variables in order to get a dynamical theory. Okay, that is just a recapitulation from our lectures of the first week. We separately derived that if a uniform kinetic system of gas molecules who are interacting just by the virtue of binary elastic collisions, okay, and then this type of gas, if they are left to relax, so for long time for example, then such a system will attain a equilibrium distribution, and we showed that this equilibrium distribution is nothing but a Maxwellian distribution. Okay, so now in this lecture we will try to see that whether a knowledge of this distribution function can help in reducing the number of unknowns. That's where exactly we ended in the last lecture, where we said, in last week, that in general, one way to reduce, so basically how can we expect that we can make a dynamical theory for a continuum, that we have to somehow reduce the number of variables. Now one way of reducing the number of variables is to find interrelations between them, and then another way is there, if in some way we can show that some variables are identically vanishing, then also in a way we can eliminate those variables, and that is again reducing the total number of variables. Okay, so in this lecture we will see that if we assume that we have a distribution which is Maxwellian in nature, okay, so sorry, which is Maxwellian in nature, then how this knowledge can reduce the total number of unknowns. Okay, in an alternative way, this is equivalent to see whether the effect of collision can lead to a dynamical theory of the collection of the particles. Okay, so this is something interesting to understand. That is, Maxwellian distribution basically becomes the most probable or the equilibrium distribution basically when the system is collisional, right, and not any arbitrary collision, but just the binary elastic collision. So if the knowledge of the distribution function, that means if the knowledge of the distribution function being Maxwellian in nature can reduce the number of variables, that means can find some interrelations between the variables, that is somehow equivalent to say that the collisions, okay, which is at the at the fundamental level the reason for the Maxwellian distribution, okay, actually helps the system attaining a dynamical theory. Okay, so that is the same thing. So in this way we will also check that whether the collisions, and actually binary elastic collisions, how these collisions can help to fluidify the system. Now the fluidify means that to make a dynamical theory for the continuum. And if you remember that our primary objective from the beginning was to develop a dynamical theory at different levels and finally to get a dynamical theory for the continuum or fluids. Okay. So now we just recall the Maxwellian distribution. Now the Maxwellian distribution is nothing but this f, which is a function of the velocity. So this is the equilibrium distribution. Okay, there is no dependence. So if it is an equilibrium distribution for a uniform gas, okay, then and also for when the system is led to relax itself, then we can easily expect that there will be no space and time dependence explicitly. So the only explicit dependence will be on velocity, and it should look like this simply: n times m by 2 pi kbt 3 to the power 3 by 2 times exponential minus m times u minus v whole square by 2 kbt. Okay, so this is this part, and where we actually assume that this n, this should be v, simply this should be v. Okay, so where we assume that this n, t and v all are constants. Now this is the distribution function of a uniform gas at equilibrium. Okay, so okay, now let us assume that our system is such that this is not exactly the above equilibrium perfect, in the perfect sense, but the particles are following in local sense the Maxwellian distributions. Okay, so what is the meaning of that? That means that the constants in t and v, they are no longer absolute constants, but they are the functions of r and t, space and time. Okay, now what is the physical meaning is of that? That simply says that the chemical, thermal and dynamical equilibria, so this is corresponding to the chemical equilibria, this is corresponding to the thermal equilibrium, and this is corresponding to the dynamical equilibrium or the mechanical equilibrium. Okay, so these three equilibria, they are established only locally. So that means within a volume element dr and during a time dt. Okay, in the neighborhood of some function of some space point r and some time instant t. Okay, so if we can, the basic supposition is that in the neighborhood of every r and t there should be some local Maxwellian distribution. Okay, that means that the velocity distribution is a Maxwellian, but these constants are now no longer constants, so they are basically constant for that specific point. Okay, but globally they are just the functions of space and time. Okay, if we do that, then we can have a local Maxwellian distribution which should look like this. So you can see there is nothing new other than just writing these previous constants n, t, v, n, t and v, okay, to be explicit functions of r and t. Okay, now for brevity, from now onwards we will simply write for any variable, arbitrary variable chi, which is this type of macroscopic quantities n, t, v, this type of thing, instead of writing just as a function of r and t, we will simply write just that function. So just when I write n, just as it is supposed that this is a function of r and t, because we are talking we are talking in the framework of local Maxwellian distribution from now onwards. So now you see, now we have the knowledge of f. So we know what f is. So now we will see how it can help in reducing the number of the unknowns. So we first calculate p tensor. Okay. So Pij, so the ij, so p tensor means this is just matrix type of thing. So its ijth component is given by m integration over the u space, okay, the velocity space. This is once again, so this is u is nothing but the fluctuation velocity. So that is easy to understand. If you just go back to the original definition of p, you will see the for a Maxwellian distribution, this is nothing but m times this fluctuation. So this is the tensorial product of the fluctuation velocities times the distribution function and then d cube u. So when this integrated over the velocity space, it gives you the pressure tensor. Okay, so the ijth component will simply be m times integration ui uj, capital Uy capital Uj, times the distribution function, the form of the distribution function, times d cube u. Okay. Now you see that here when I just write this type of a single integration with a u vector, it simply means that this basically denotes 3 integrations over 3 components of u. Okay, and all the integrations will vary from minus infinity to plus infinity. Okay, so you see from this type of expression, you will simply understand that Pij vanishes if the integrand is odd. Okay, and how is that possible to understand? Just a minute. Yeah. So you see that this part is an even function of u, that is u square. Okay, now this part you have 2 different components. Okay, so of course these things we even don't know how should they be, but if this part will have an odd part, then the total thing will be an odd function. And as the whole integration is within minus infinity to plus infinity, then anything which is odd inside will make the whole thing vanish. Okay, that's very easy to understand. Now since the nature of the integrand depends on ui uj, what I just said 5 seconds ago, evidently Pij vanishes when I is not equal to j. That means when we have this type of combinations ux uy or ux uz or ui uz. Okay, now please check. So basically due to the lack of time constraint, it is not always possible to do every single step of the lengthy calculations, but it is highly recommended or highly suggested that you check all this calculation at home. That is the only way to learn. Okay, so please check that if you have, let's say you just take this combination ux uy, then basically you are calculating nothing but pxy, the xy component of the pressure tensor, and this will be given by this. Okay, and you see that this integration, for example, when you so basically x is not equal to y, so this is a case where I is not equal to j, so you can easily check this is 0. So I leave it on you as an exercise. Okay, so basically you have to remember that u square means what is yeah, so basically you have to remember that u square is is nothing but ux square plus uy square plus uz square. Okay, and d cube u is nothing but dux duy duz. Then you just use your knowledge of integration and you should find 0. If you don't find 0, that is a problem. Okay, then please let me know. Now the integration of course does not vanish in case I is equal to j. Why? Because we can show, and that's exactly here I have shown, that if I is equal to j, then what happens? Then it will give you something, a square of something. So for example, if x is equal to y, then it will be ux square, for example. Okay, now I showed here how it should and what will be the value. If it is non-zero, then what should be the value of it. So the integration will then be simply pii, and it will be given by mn times this whole factor times integration. Okay, so mn this whole factor times integration uy square times exponential minus mu square by 2 kbt times d cube u. Okay, now we again take a proper, like a particular example, I is equal to x. Then this integral is nothing but this. Okay, and if you have this, now you can simply see that this ux square will go to this part of the exponential. These other two parts will simply be just integrated within minus infinity to plus infinity. Okay, so we will have at the end this I is equal to integration minus infinity to plus infinity ux square e to the power minus mux square by 2 kbt times d cube x. Okay, and then for y and z we will have the same type of integration. So we will just write one integration of this type and we will square that. Okay, so that is the square. So this is exactly what we did, and you know that this type of integration has a very simple formula. So in integration over from minus infinity to plus infinity, if it is simply e to the power minus beta x squared dx, then it should be simply root over pi by beta. Okay, and that's exactly what we did here. Okay, you will see. And what about this integral? That you have to do. So right from the first assignment, I tried to train you in doing this type of integrations. Okay, and in the standard books, the reference books which I told you in the course handout, you can see, or in the any standard mathematical physics book, you can see this type of integrations are done there. And if you do this correctly, you will see this will give you simply something like this. So the total, so that this total integral times this, okay, will be this, where this one, so just for in case you are, so this one basically is 2 pi kbt by m, and this one is the rest of it. Okay, so yeah, the rest of it you can just do that. Okay, so if you do it like with proper care, and finally just again replacing this, so this is nothing but, if you just remember, this is nothing but pxx. Okay, and this pxx xx, if you just remember, this was nothing but this factor. Okay, this was nothing but this factor times this integration. Okay, so this will be then this factor times this integration value, which is now calculated. And if you do it carefully, you will see that this pressure is nothing but in kbt. Okay, so this is something you already know maybe from your previous knowledge of kinetic theory. Okay, if you don't know, you learn here. Okay, so in the same way, if you calculate pyy and pzz, you can actually see, if you, even without calculation, if you think a bit, you will see that that will also give you the same thing, and this will be again in kbt. Okay, so the conclusion is, for our case, the pressure tensor, okay, is such that it is 0 when I is not equal to J and it is equal to P, which is equal to NKBT. N is the density, T is the temperature, KB is the Boltzmann constant. Okay, so basically, if you want to write the pressure tensor roughly, it should look like this: PPP 0 0. All the off diagonal elements should be 0 and all the diagonal elements should be P, where P is equal to NKBT. Okay. So a compact way of writing such type of tensor is nothing but this: Pij is equal to small p delta ij, where delta is the Kronecker delta. Okay. Now we have to calculate the, so for P, basically what we see that we had 6 unknown variables. Now we have only one unknown variable to handle with. Okay. Now we have to calculate the heat flux vector Q. Again, we go back to the definition. So the definition is Q is equal to half m integration minus infinity to plus infinity capital U square times capital U vector, okay, times F d cube U. Okay. So for a Maxwellian distribution, it should look like simply this: Q is equal to half m integration U square, I mean capital U square capital U vector times the total Maxwell-Boltzmann distribution, this, okay, times d cube U. Now you see this part is, again you can see, is an even function of U, okay, for all components. What about this part? This is an even function, but from here you will always have an odd function. So how to check that? You again take one component. So let us choose Qx. Then what it should, how it should look like? It will simply be m by 2 integration U square times Ux, then the whole thing of this distribution. Okay. And U square, you can write Ux square plus Uy square plus Uz square times Ux. Okay. So you will see that now we will have the products of 3 integrations. So for Uy and Uz, you will have non-zero things because that will be globally an even function. But for Ux, you will have Ux cube, and which is an odd function, and from this part you will have Ux square all as a function of Ux square, so it's an even function. So basically this will be an odd function. So all the 3 terms will contain one odd part. Okay, so you will see that if you just so basically you now can see that you will have 3 integrations. So if you just want to check it, so just from here to here, that will be m by 2. So integration into this, if I just write Ux cube, okay, so plus Uy square Ux plus Uz square Ux, okay, times an even function, okay, times an even function. So this is this even function, this one, okay, this is the even function. Okay, so this is an odd function. So when I just take the first one, you will see that this Ux cube gives me the odd function, and for the Uy and Uz I don't have any odd thing, but finally I have one odd part and that will give me 0. Then for this integration, so that will be a sum of the 3 integrations. For this integration, again Uy squared Ux give me an odd part and this will give me 0. Again for the third one, Uz squared Ux give me an odd contribution, so which makes the again the integration to be 0. So finally the thing is that Qx is 0. For the same reason, Qy and Qz can also be shown to be 0. Okay, let me just clean out these things. Okay. So there is a big relief that we have somehow eliminated a total vector. So already for Q, already for P, we have reduced 6 variables to 1, and for Q, we have got rid of 3 components because it is identically vanishing for Maxwellian distribution. Okay. Now recall, now try to understand the last one, which is epsilon. What is that? By definition, this is 1 by 2n integration minus half to minus infinity to infinity capital U square f d cube u. Here I am again suggesting that when I am writing this type of equation, please check that to the equation in the previous lectures and try to match them, that whether they are consistent with each other or not. Once again, anything which is written within angular bracket is equal to, so something, let's say I am writing, let's say u square angular bracket. This is nothing but integration u square minus infinity to plus infinity f du, okay, by n. So if I just want to, for example, make a reference for this integration, it will simply be n times this angular bracketed u square. Okay, so just keeping this in mind, try to check whether this is the this is consistent with its primary definition or not. Okay, so if you correctly do the algebra and integration, that is very important. If you have to do correctly the algebra and the calculation, then you should get epsilon is equal to 3 by 2 kBt by m. And you see that is something very expected. So the kBt has a unit of energy. So this is a unit of energy per unit mass. So this is a unit of velocity square. Okay, and that's very easy to check from here as well, because integration f d cube u has a dimension of density, so has a unit of density. So this by this density will go off, and you will have, it will have a unit of u square. It's a velocity square, that is the energy per unit mass. Okay, so this is a fabulous exercise to do at home. So try, take f as Maxwell-Boltzmann distribution and calculate integrations carefully, and you will see that your E will be, epsilon will be equal to 3 by 2 kBt by m. Of course, 3 by 2 factor comes for monoatomic gases. Now what will be epsilon for a gas with more molecules having f degrees of freedom? That will be simply f by 2, because for monoatomic gases they have just 3 degrees of freedom. So 3 times half kBt by m, that is the formula. So when f degrees of freedoms are there, so f times half kBt by m, that will be the formula. Okay, so now I have a question for you. There's a small task. From there, how to find this epsilon for for diatomic molecules? Okay, then you have just to find the number of degrees of freedom. That's quite simple. Okay, so finally you see that we have calculated also epsilon. So what else? Finally, if you remember, there was a term of double contraction in the energy equation, and that was the double contraction of P tensor to lambda tensor, where lambda is the symmetric part of the velocity gradient. Okay, so now in case our Pij is equal to some small p times Kronecker delta Ij, for this simplified case of Maxwellian distribution, of course local Maxwellian distribution, don't forget that, then this contraction is simply equal to Pij lambda ji. Okay, and from Pij lambda ji, finally you can also write lambda Pij lambda ij, because lambda is symmetric. Okay, so if I now expand and for lambda ij and put the value of expression for Pij for our current case, we will see this is nothing but half P Kronecker delta Ij times del Vi del Xj plus del Vj del Xi, which is equal to P times divergence of V, simply because Kronecker delta Ij will survive only when I is equal to J. So simply you will have here half P 2 times divergence of V. So that will be P times divergence of P. Okay. And what is this divergence of P tensor? When P is diagonal, like this, P, P, P. Okay. So through along the diagonal, it has the three identical values P. So the divergence of this tensor will simply be the gradient of this scalar value. Okay. So divergence of curly P tensor will be equal to gradient of small p, which is the eigenvalues of the P vector, P tensor. Okay, pressure tensor. Now, collecting all the previous expressions, finally we can write the momentum equations to be del V del T plus V dot nabla V is equal to minus gradient of P by rho plus G. Okay, G is nothing but the acceleration due to the body force. I wrote G because most of the cases in astrophysics we use the case or the framework where the body force is the gravity. So this is just the gravitational acceleration. Okay, you can write any other symbol. Okay, and the energy equation now becomes the internal energy evolution equation, del epsilon del T plus V dot nabla epsilon is equal to minus P by rho. So this will be again, I'm sorry for this. This will be again small p by rho, okay, time divergence of V. Okay. Now you see, we should not forget this continuity equation, that is the third equation. So now you see we have 3 equations. This is a vectorial equation, so this basically means 3 scalar equations. So we have 5 scalar equations. So we have 5 states. For example, Vx, Vy, Vz, epsilon and rho. And how many variables or unknowns we have? We have V, we have P, we have rho. So G is given. So this forcing is known. That we don't worry about. Okay, that is not something to be worried. Okay, so V, P, rho, epsilon. So V has 3 unknowns and then P, rho, epsilon. So we have 6 unknowns. Okay, now we are almost there. So we had 14 unknowns, 5 equations. Now we have 5 evolution equations, 6 unknowns. We are almost there. Can we be achieving the dynamical theory? The answer is, well, let's see. So you see the previous equations. So after this, basically the previous equations constitute a system of 5 equations, I just said, and so this gives you 6 variables, but we really need 5 variables. How to do that? That is exactly if we just write the explicit expressions of rho, P and epsilon, small p and epsilon, we'll see that these 3 basically are related by only 2 variables, n and t. So rho is equal to rho of n, p is equal to p, which is a function of n and t, and epsilon is equal to epsilon n and t. Okay, so there will be a comma. Yeah. So you can actually just express p in terms of epsilon. Okay, just in terms of epsilon and rho, to be very precise. Yeah. Okay, that is a small homework for you. So just eliminate n and t to relate p, rho and epsilon in a small simple algebraic relation. Okay, do that. But at least from this one, without calculating any further thing, it is now evident that we have 5 equations and 5 unknowns. Hey. So we have a dynamical theory finally. So we have 5 state variables. Okay, and we have 5 evolution equations. Okay, and this is known as then the system of the ideal fluid equations. Because why it is ideal fluid? So till now we have just seen that this is the first time we have developed a dynamical theory for a continuum. So we even don't know whether this is called an ideal fluid or not, but the equations which we get from the previous knowledge of the so from the so from the previous knowledge of the fluid engineers or fluid mechanists, so this is somehow very evident that these are nothing but well-known ideal fluid equations. Ideal fluid means a fluid which does not have any type of transport properties. So what are the transport properties, that we will try later. So for example, I am just trying to tell you something, okay, so which is easier to understand. For example, a fluid which does not have any type of transfer of density from one point to the other, neither any form of viscous effect, okay, in case you already are familiar to fluid dynamics, okay. So and also it does not have any conductive property, for example thermal conductivity type of thing, okay. So if we have a fluid like that, which is not a practical fluid in general, but it's called an ideal or perfect fluid, okay. So this is then the equations of the perfect fluid, okay. So basically here where we end our this current part. So in the next part we will discuss some properties of the ideal fluid, and we also try to understand that how one can look at the ideal fluid and its equations from a macroscopic point of view, okay. Thank you very much.